Hey everyone, this is the video for 7.3 notes, which is intro to logs, inverse logs, and graphing. So in our previous two lessons, we talked about inverse functions, like what does it mean to be an inverse function? How do we find those things? And we also talked about exponential growth and decay. So how to calculate something that grows at a specific rate or decays at a specific rate, what those might look like on a graph, and things like that. So to get us started, we're going to kind of go back to the exponential growth idea and take a look at what we would need to do to graph that. So for the most part, anytime you're told to graph an exponential, or at least for the purposes of class, we're just going to have a t-table. So we set up a little t-table here where we have some values for x's, which they gave us like a nice range of values here, and we are going to find the y. So basically, we're just going to take each of our x's, plug them into the exponent. So we're finding 2 to the x power, and that's going to give us a series of points that we can then plot on our graph or on our grid. So for this first one, this is a -3, so it's 2 to the -3 power. If we simplify that, so you do kind of have to remember some exponent rules here. So your exponent rule for negative exponents, your value should turn into a fraction. It's going to make your number really small, so this becomes 1 over 2 to the third. And then if you simplify 2 to the third, that becomes 1/8. So one of our points that we're going to plot is -3 and 1/8. Okay. Now we do know we have a whole 3 or a positive 3, so you could also do 2 to the third power, which we already just found. That would be 8, and that means we also have the point 3/8 to plot. Okay. The next point, so 2 to the -2 power, that would become 1 over 2 squared, and 1 over 2 squared would become 1/4. So our next point would be -2 and 1/4. And just to kind of do the opposite of that one, so 2 to the +2 power, that would become +4. 2 to the 4 would be another point. The next one, 2 to the -1 power. If I change that into a fraction, it's 2 to the first. Well, 2 to the first is just 2, so 1/2. So our point would be -1, 1/2. 2 to the first power is just 2. So we also have the point 1, 2 to plot. And lastly, 2 to the 0 power. 2 to the 0 power, well, it's the same as anything to the 0 power. It should always be a 1. So the point 0, 1, that's going to be a pretty common point among our exponential functions, just to kind of keep that in mind. Okay, but now I can go and plot each of these points. So I'm actually going to start with the whole numbers at the bottom. I figured it's a little quicker for us to process those. So 3, 8 would be right 3, up 8 on our grid. We'll go right here. 2, 4, right 2, up 4. There's a point. The point 1, 2. So right 1, up 2. There we go. And 0, 1, 0, 1. Okay, and those are all the points that deal with nice whole numbers. Okay, when it comes to the fractions, so if you take a look at each of these fractions, 1/2, 1/4, 1/8, all of those are between the values 0 and 1. Okay, so if I want to go plot the point -1, 1/2, so -1 I know is to the left 1, but 1/2 needs to stay in between 0 and 1 in this y direction, so I just need to put it between 0 and 1, and 1/2 is somewhere in between those. Okay, if I have -2 and 1/4, I need to go left 2. Again, 1/4 is somewhere in between 0 and 1, so I just need to plot it in between. I don't necessarily have to like estimate what a fourth is, but if you want to, you can. Depends on how zoomed in, I guess, you want to get. And for this last point, -3, 1/8, so left 3, 1/8 is also between 0 and 1. So we would plot it somewhere around there. The main idea is all of these fractions, any fraction you end up with, should end up between 0 and 1. You don't want them to dip below the x-axis. Okay, that's something we don't want to happen, or at least when we're graphing the exponential version. If we go to connect these, so what it's going to look like, it'll be a curve. It's a curve that looks like it's growing very slowly, like this goes to the left forever, but it goes to the left and it stays above that x-axis. Okay, so that's why I say it has to be above the x-axis because it won't dip below in the negatives. And then when it moves towards the right, it grows very quickly, and it goes up forever and ever. It looks like it's going to go up vertically, but it does have a slight curve to it. It's just hard to see when you're this zoomed in. All right, and that's what our exponential functions will look like for the most part. So we'll start by creating a t-table to find the points. We'll plot those points, and we'll connect the curve. Okay. Well, last week when we started talking about our functions, we talked about exponentials a little bit when we talked about growth and decay, but we also talked about inverses. Okay, so while you guys might be familiar with an exponential function and what it would look like and what it does, you may not be as familiar with its inverse. Okay, so keep in mind, in order to graph an inverse, like if I wanted to graph something that was the inverse of this, all I'd have to do is switch these points over here, flip them, plot the new points, and we'd have the inverse function. I'm going to hold off to do that here for a second because I want to talk about what the inverse of an exponential is. Okay, oh, whoops. And of course, it's acting up. Okay, so the inverse of an exponential is called a logarithm, or for short, we'll call it a log. Okay, so we could also call them logarithms. This is like the full name of the function, a logarithm, but we'll call them logs for short. And they are the inverses of exponentials. Okay, so those, what we kind of talked last week or in the previous lessons in math, there's always kind of an opposite or an inverse of something. You have to, if you do something, you have to have a way to undo it. So logs and exponentials are the inverses of each other. Okay, and here's kind of how we could set them up or what they might look like as far as notation goes. So for our exponential, there's always a base number, right? And it's always to some power, and this is where our variable would go. So I'm going to call it b to the x power. That would be how the exponential is set up. And it would equal a y. So b to the x equals y is how we would write an exponential. Okay. In order to find the log, or rewrite this as a log, because essentially, kind of like in the last unit where we took our rational exponents and we changed them into roots and vice versa, we can do the same thing with logs and exponentials. We can rewrite them and they would be inverses of each other. Okay, so the logarithmic function. Surprisingly, there's no actual symbol for a logarithmic function. It's just the word log. Okay, so we'd have the word log. It has a little subscript for a base. So the base number in the exponential is the same base number we have over here in our log. So this would be log base b. You take the log base b of some value. Well, here is where our x and our y will switch places in our exponential. And it would be log base b of y equals x. Okay. So that's kind of how things would be set up, how we change one to the other or go the opposite way. And if it helps to have like a little phrase to remember the order that things go in, you can try to remember first, last, second. Okay, it kind of helps with the order of things, like this would be first, this would be last. Well, here, this would be first, this would be last, this would be second. And so when you move it around, here's the first, here's the last, here's the second. You could also go the opposite way. So if you were trying to change an exponential, or sorry, try to change a log into an exponential, you would go first, last, second, and that would be the order that they would go in the exponential. Okay. All right, so we're actually going to practice that a little bit, how to rewrite these log functions into exponential functions. So if I get started here, log base 2 of 32 equals 5. So that's how we would read it out loud. Log base 2 of 32 equals 5. If you look at the way the log function is set up, the base is what becomes the base in the exponential. So if my base is 2, that means 2 becomes my big number. The exponent, or the next value here. So we have the y here. But if the y is the thing we're supposed to equal over here, that means the 32 is what we should be equal to. Okay, this is our y, which means our exponent, or our x, would be the 5. So 2 to the 5th power equals 32. That's a true statement. That's something that you should be able to verify. And as long as you do, then it should be fine. So 2 to the 5th power equals 32. That's, that's an exponential form now. Okay, I would highly recommend trying the other ones, and pausing and taking a second to work on them, see if you can rewrite them in the right order. But if you're ready to go, here they are. So I have log base 5 of 125 equals 3. So my base number would be the 5. My exponent would be the 3, and that would equal 125, which is true. 5 to the 3rd power is 125, so that is all in the right order. Next one, log base 7 of 7 equals 1. So the base is 7, the exponent is 1, and it should equal 7, which is also true. So the last one, log base 3 of 1/9 equals -2. So my base is 3, my exponent is -2, and that should equal the 1/9. Okay, and that should check out because in the warm-up we talked about negative exponents becoming fractions. So all that looks like it's in the right order. Okay. All right. So here's what this is kind of getting us ready for. Okay. As far as logs and exponentials go, we know that they're inverses of each other. So we should be able to find inverse functions if we're given one or the other. So this kind of follows from finding our inverses of last week. They're the exact, 2 same steps if you try to remember those steps. So in order to find an inverse, the first step is switch x and y. Okay. And then the second thing is solve for y. Make sure you get the y by itself. Okay. So those steps are still the same here when it comes to logs and exponentials. You just want to make sure you look carefully, or you write things in the correct order, so when it helps whenever you are solving. Okay. So for this first example, if we were to walk through log base 11 of x equals y. Okay, based on all of our inverses, the first step is to switch x and y. So these 2 letters switch places. Everything else stays the same. So it's log base 11 of y equals x. That's how we would write it out. Okay. Now here's the deal. In order to solve for y, right now y is inside our log function, and we have to make sure to get it out of the log function so we can get it, on its own. And this is where we have to use its inverse. So if logs and exponentials are inverses, I'm going to change this equation into an exponential. And ideally, that would be what the inverse should look like. So if it's log base 11 of y equals x, my base number is the 11. My exponent is the x. And I would set that equal to the thing we're taking the log of, which is y. And if you notice, so it says to solve for y. Well, the y is by itself, which means it's solved for. This is my inverse function. So this is just to kind of show you too, logs and exponentials should be inverses of each other. These are opposites or inverses. Okay, like if you have to find the base, if you have to find the inverse of a log, you should not end up with a log. Okay, you should end up with some kind of exponential function. Okay. So again, I would recommend maybe pausing the video and trying the other 2. But if you're ready, we're going to go through number 2. So it's y equals log base 2 of x. For my first step, I switch the x and y. So this becomes x equals log base 2 of y. Okay, y is inside the log. If I need to get it out, I need to rewrite it as an exponential. So my base number is going to be the 2. I'm going to put it to the x power because that's on the other side of the equal sign, and it should equal the y, which is now by itself. So here's our inverse function. So 2 to the x equals y, its inverse would be log base 2 of x. Okay. And for this next one, y equals log base 9 of x. Switch the x and y. X equals log base 9 of y. To get that y out, I write it as an exponential. So 9 to the power of x equals y. Y is by itself. So here is our inverse function. Okay, so that's also just to kind of get you used to looking at the fact that logs and exponentials are inverses or are opposites of each other. So therefore, if you start with one, you should end with the other. Okay. The next few examples. So we're still doing the same thing. We're going to be finding the inverse functions of these logs. There just might be an extra step or so that we have to consider or pay attention to because it is important for us to pay attention to these things. Number 4. So the problem is log base 3 of x plus 5 equals y. So first things first, switch the x and y places. Okay, log base 3 of y plus 5 equals x. Okay, remember only the letters switch places. Nothing else should move. All right, and if we need to solve for this y, so remember I got to change everything to an exponential function. Well, my base is the 3. I always need to take it to the, well, whatever the thing equals, power. So this is 3 to the x power equals, the stuff inside the log is the y plus 5. Both of those are inside the log. But here's kind of that final question. Is this y by itself? And it's not quite by itself yet, right? There's a little bit more solving we have to do. If we have a y plus a 5, that means we need to subtract 5 from both sides to get our final answer. And right here, when I go to look at these, 3 to the x power minus 5, well, those are not like terms, right? One has an x and one doesn't. So because they're not like terms, we just literally write this out. 3 to the x power minus 5 equals y. And here's our inverse function. Okay, there's still inverse things that you can double check for, like the original problem had a log. This one has an exponential. The original had a plus 5. This one has a minus 5. Okay, that's how I know I'm using the right stuff. Example 5. Y equals log base 7 of x minus 8. So if I switch the x and y, it becomes x equals log base 7 of y minus 8. Okay, I need to get the y out of the log, so I need to rewrite it as an exponential. This becomes 7 to the x power equals y minus 8. And finally, to get the y by itself, I need to add 8 to both sides. Again, I cannot combine these things. They're not like terms, so this becomes 7 to the x power plus 8 equals y. And there is our inverse function. All right, last one. Y equals log base 5 of 6x, switch the x and y. X equals log base 5 of 6y. In order to change this to an exponential and get the y out of the log, I need to write 5 to the x power equals 6y. Well, keep in mind, I don't see a plus, a minus, or a division. This is 6 times y, so to cancel out the 6, I need to divide it from both sides. I can't divide a 5x by a 6, so I'll just leave it as a fraction. 5 to the x power over 6 equals y, and there's our inverse function. Okay, so those are all pretty straightforward. You're just finding the inverse function. Again, that's not going to be an x equals a number or a y equals a number. You're just trying to get the opposite type of equation to look at. But that's going to lead us into graphing. So we graphed an exponential in the warm-up, but we haven't talked about graphing a logarithm. Okay. typically, whenever we go to graph these functions, we will graph them both. And we'll look at them at the same time because we know they're inverses of each other. And if you can graph one, then all you have to do is switch the points and graph the other. So this does say to use a t-table like we did in the first one. So I'm going to create a t-table. Let's see here. I'm actually going to use the same x values as I did before, but I am going to go in the positive order first. So 3, 2, 1, 0, -1, -2, -3. If you're not really sure where to start, these are always a good basis to cover if you're looking for numbers to plug in. And then we're going to plug them in to get y. So keep in mind you're taking 3 to the power of this number. So 3 to the third power, that would be 27. And again, these positive numbers have negative values also, and that's just where they become a fraction. So instead of 3 to the -3, we can just put 1 over the 27. Okay, maybe kind of save us some time here. 3 to the second power, that is 9. So 3 squared is 9, which means 3 to the -2 power is 1/9. The next row, 3 to the first power, that's 3. So 3 to the negative first power is 1/3. And then lastly, 3 to the 0 power, that is 1. And now I have a list of points I can plot. So I can plot the point, well, I can try to plot the point 327. If I go right 3 and I try to go up 27, 27 is who knows where up here. If it's not on your grid, don't worry about plotting it, okay? We're not going to worry about 327. It's not going to fit. Let's try 2, 9. So right 2 up 9. That one does fit. So we need to make sure we graph it. We got that one. 1, 3. So right 1 up 3. That we can graph. 0, 1. 0, 1 is right here. That's a pretty common point for our exponentials. So that's one we'll graph. And then remember, when it comes to these fractions, just do your best. So I know I need to go -1, but 1/3 is between 0 and 1. So I'm going to plot it somewhere in between there. Okay. -2, 1/9. So left 2, 1/9 is between 0 and 1. So I'll plot it just above. And then -3 and 1 over 27. So -3, 1 over 27 is also a fraction. So remember, they will hover right above that x-axis, but they will not go below it, and they will not go above 1. So when I go to connect these, make sure it does have arrows on both ends because it does go on forever and ever, even if we only see this little snapshot of it. Okay, and there's our exponential function. Okay, now to talk about our inverse function. Okay, our inverse function is this log base 3 of x. Okay, and here's the thing. We don't really know how to plug numbers into our logs yet to understand how to get points if we try to make our own t-table. So what we could do, if you use all the points that you already had, just flip the x and the y, and we'll get our inverse points. Okay, should work the same way. So if I flip 3 and 27, becomes 27, 3. And again, that's not something that's going to fit. It's going to go way over to the right. So we can't actually graph that one. Just ignore it. But the next one, 9, 2. I can graph that. Right 9 up 2. There's my point. The next point, 1, 3, becomes 3, 1. If I go right 3 and up 1, there's my point. The next one becomes 1, 0. So 1, 0 ends up right here. The next point, 1/3, -1. Okay, now here I get into those fractions again. So keep in mind, 1/3 is between 0 and 1. So I know I'm somewhere in between the y-axis and this 1 right here, but I need to go down to the -1 level. So it's just somewhere in between the 0 and 1 to the right of the x-axis, or the y-axis, sorry. Same thing for the next one, 1/9 and -2. So I need to go between 0 and 1, but I need to go down to 2. Plot a point. Then the last one, 1 over 27 and -3. So between 0 and 1, but down to -3. Okay, so that way, this time when I graph them, they're going to hover really close to the y-axis, but not go over. And then it's going to curve over to the right. So in log functions, again, these should be inverses of each other. Like if you fold them on the diagonal, they should line up. When it comes to graphing log functions, they look like they're going to grow very quickly, like they are almost vertical when you start, but then they're going to turn and curve off and kind of level out to the right. Okay, that's kind of what that'll look like. Okay, and that's how we would graph an exponential and its inverse, the log function. Okay. One more of these we're going to practice with, and then we'll be done. Unfortunately, it looks like these grids kind of went off, but I don't need too much of this, so let's actually go ahead and set these up. So if I use the values 3, 2, 1, 0, -1, -2, -3. Okay, this time our exponential is y equals 5 to the x power. Our inverse is log base 5 of x. Okay, so I'm plugging these values in. So 5 to the third power, well, that equals 125. Okay, 125 is way bigger than our grid. We will not be plotting that. Okay. 5 to the second power, so 5 squared is 25. 25 is not also not on our 5 by 5 or on our 10 by 10 grid, so we will not be plotting it. 5 to the first power, now that is 5, and that is a point we can plot, so we will plot 1, 5, right 1, up 5. There's our first point that we can actually put on our graph. The next one, 5, 0, that is 1, so 0, 1 is the point. It's right there. And now, thankfully, these negatives, you can kind of flip the positives into fractions, and it should work. So 5 to the -1 power is 1/5. 5 to the -2 power is 1 over 25, and 5 to the -3 power is 1 over 125. Okay, so some really small fractions here, but again, all of these fractions are between 0 and 1. So if you just place a point between 0 and 1 right above the x-axis, you should be fine. So we'll start with the -1 and 1/5. It would go about here. -2 and 1/25. Go about here, and then -3 and 1/125. That's a very, very, very small fraction. But again, we're not going to be super picky when it comes to graphing. We just need to make sure it stays above the x-axis. So I'll graph these with a curve. Again, notice it's the same type of curve as before. They should always kind of look like that. And now I can take each of those points, flip them, graph the y. Now here's the thing. If I couldn't graph 3 and 125 and 2 and 25 the first time, probably not going to be able to graph them the second time. So let's skip those. Let's flip this 1, 5. It becomes 5, 1. So 5, 1 goes right here. This is the point 1, 0. So 1, 0 goes right here. 1/5 and -1. So again, stays between 0 and 1 to the right, but it needs to go down to -1. The next point, 1 over 25 and -2. So down to -2, but really close to the y-axis. And then the last one, 1 over 125 and -3. My -3 almost got cut off, but it's kind of almost right there. So I just need to connect those with a curve, and there we have our logarithmic function. Okay, so I know that's kind of quick. If you have any questions about any of that, please let me know.